better?
Yeah.
It is, isn't it?
Yeah, I know. When I opened it, I saw all of those things. I was like, oh my gosh, I'm so excited for this.
Well, I'm just gonna never I did the same thing. So I'm trying to do, 'cause a lot of these are new assignments for me, and so I'm trying to do at least almost all of them. Every once in a while I'll skip a problem that I know how to do, those types of things, but I'm trying to sort through and make sure that I'm gonna use those and so on. So anyway, so it's become a burden for me too. And then, so I hated it every time I opened it.
Or malware, but it's, you know, still can be really unwanted and be popping up all the time. So
Yes, definitely.
yeah, they don't think it's malicious stuff.
Oh, good. Well, I'll just ignore it and close it until it goes away, right? I'll figure out how to turn it off. All these new things you have to learn how to do in the modern world. Which reminds me, I've got to approve a document in the modern world. I gotta remember to post your live quiz for next week, and then post your lecture for today, from today. I do a lot of posting anymore. Used to be as paper assignments. Oh, the graph, yes, I absolutely. So. Anybody have some data I can borrow? I should have temperature. That's in C, right? And then the next one is. Oh, look at the copy right back. And temperature, and then it's the mole fraction, right? Or volume fraction, excuse me.
Yes, it says hot temperature. Oh. It's one or the other. It's just the stuff that was on the ground.
Did the last one ever come out? So we're gonna leave that one off. And then volume fraction.
I actually did the other day. Me too. Dude, I want to go there and my sandals on. I was like, I didn't need to. I mean, I'm not like, do I want to hold you?
Like, give him like 5
Alright, here we go. Housekeeping. Let's do that first so don't forget. And remember, we're reading chapter 2, so if you log on to Achieve and you open up chapter 2, then you can work through each section of the ebook or chapter at a time or section at a time. And so these are the sections, and just to show you that I want to read one of those, I can click on that and read through that. And then it's also connected with your homework. Just a reminder, in addition to that, then I redid the beginning. If you look at your grade book, then what you'll notice is that I can't open that in front of class because it would show everybody's grade. And we don't want to do that because that's a FERPA violation. But if you open it, then what you're going to find is I added a category for extra credit, just a new column, and I gave everyone 30 points. Okay, is that fair? All right, so that takes care of the disorganized beginning. It shows the assignments that are currently due. Nothing is past due right now, so if you just now got signed up, you still have time to complete that work. Okay, I'll add another day or two if you need it. Cool? These, or actually I say that, these 3 are closed. They closed this week, so I will open those back up if you need me to. But anyway, and then this one will close on the 10th, these are the 13th, the 17th, and then it also gives you those point values associated with them. All right? I'm going to put some practice tests up, and those are what I'm going to make extra credit, okay, for each section. And so to recoup points that you would lose doing your homework, then you'll be able to take the practice test to get ready for the quiz or exam that are coming. Cool? Okay, that's the plan anyway. Does that sound like a good plan? I think I've got this figured out now, so I'm getting a lot more comfortable with it, and so I hope you guys are too. All right. Any questions on that? I had promised that I would go over how to do the Excel sheet for this week's lab, which was a phase diagram. And so we're going to create a graph, which is temperature versus the volume fraction. I believe the temperature should go on the y-axis because that was the experimental response to the ratio that we made, and so that would be the appropriate way to graph that, unless I've stated otherwise. But that's, without looking, that's what I'm going to call. Is that good? All right. Now, I don't have the volume fraction yet. I just have the pieces of each. Now, Excel doesn't keep my significant figures for me, just to let you know that. Okay? It just truncates the number if there's a 0 on the right-hand side. If I put in 3.0, then it would just put 3. So just to let you know that. Now, to do a volume fraction, I'm going to show you guys something that makes Excel wonderful. Okay? Now, it takes a little practice over time. Some of you may already be able to do this, but I'm going to use an equal sign. Can you guys see my equal sign up there? And let me escape that. Just a second. I'm going to blow that up a little bit more. Does that help? All right. And so I'm going to put in an equal sign. And I'm going to write a formula. Okay? Now, I need the volume fraction of acetylacetone. And so I'm going to put equals the acetylacetone, right? And so I'm using a cell, C3, because that's my first acetylacetone number, right? And then I'm going to divide that, and I'm going to parenthesis because I want to do a order of operation and make sure it gets done correctly. And I'm going to put that same cell plus the cell beside it, which is the water. Okay, so that equation, right, is in the first page of your lab. You actually did it in the lab quiz. And so the fraction acetylacetone is equal to the right, and we're just gonna do these in the milliliters, right? And so, in this case, I had 3 milliliters divided by 5 milliliters. Cool, you guys with me? Yeah, which is 1/2, isn't it? So 0.5. And so, the neat thing I can do is I only have to type that once, and I can go to the box, drag down, and it will calculate all of those values for me. Yep.
It's supposed to be, what is the C line? Is that a different?
There's a volume fraction here, and this is a different column. That's the volume of acetyl acetone that I used in milliliters. So you should have a table that looks like this, right? Now you actually had volume initial and volume final, and I could actually put those in there and do my calculation to find the volume from each one of the deliveries. Does that make sense? But I took the total volume, which is the third column for the 2,4-pentadione or acetyl acetone.
Oh.
Those are the same compound. Okay? 2,4-pentadione is the same compound as acetyl acetone. It says that somewhere on the front page. Or I thought it did. That's the common name for it. Okay, so a lot of things have common names. You with me? And so that's one that is classically used by a chemist. All right? All right, so anyway, so I'm using, so I can change that if you would like to make that clearer. How's that? Oops. Cool? Fixed. All right. I apologize for that. All right. Now, I calculated the volume fraction so that I could graph it, correct? And so I did that, and now I'm going to graph. Now, I want you to notice there's one spot up there that says unknown. For many of you, that last data point may not have come out, right? And I noticed that these young ladies had put a 0 there, but you didn't get a temperature, so you really can't record 0. That would be incorrect. Does that make sense? So my opinion would be that you would write or unmeasurable, non-measurable, something along that line. Okay? So that means I'm not going to plot that point. I'm going to leave it off of the graph because I don't have a data point for that. And so I'm going to plot this section, and I lied to my first section for sure. My second section, I tried to correct it, but not everybody was listening. And so I said, don't use a scatter plot, use a line plot on this. I lied. Okay, I was thinking of a different lab, and this one we're going to use a scatter plot on. So we're going to take our data, we're going to go to insert, and we're going to go right back over here to the one that has the dots, and it says insert XY or bubble chart. Okay? And XY scatter or bubble. And so I'm going to click on that, and I'm going to click on my data, and it's going to throw it onto the graph. Okay? Now, I want you to notice something. What did I say should go on the y-axis? Temperature. I want you to notice that I put temperature on the left, and XL puts that as X. That's its default. And the right is Y. And I put the Y on the left. Now, is that big a deal? No, I can either switch the data boxes, or I can go right click on a data point, format data series, and should have popped up right there. Am I on the web version of this stupid program? I must be. Oh, I hate that. There's nothing more. Do what?
If you click either like the data or the
Select data, that's what I actually wanted. So I'm going to edit my data, and so what I want to do is change these values to B, and these values to A. You guys with me? Oops. And so right now I'm just flipping those axes. And so anyway, so now that's done, and I click OK, and that's the shape I expected. Okay, so now I've got my temperature on the y-axis and my volume fraction on the x-axis. Cool? You guys with me? And then just like we did last week, you're going to go in and make sure that you have axis titles, and you would title those temperature and volume fraction. Be sure to put the units on there C. And so I'll let you guys, and then I want you to name it. The last part, we're going to actually put a trend line on this. Okay? But instead of doing a linear trend line, we're going to do a polynomial. Okay? You guys know what a polynomial is. What would be an example of that? Parabola, quadratic formula, right? And so when we do this, we're going to do a polynomial. That's actually a quadratic expression. The order is second, right? I might be able to make that a little bit better fit by going to third order. And that looks pretty good by eye, doesn't it? All right, so, and then we're going to display that equation and the R value that fits at 0.997. What's a perfect fit? 1. Okay, cool. You guys with me? You guys good with that? Yeah. Is it nice to see how you write an equation?
So,
Yeah, go
where
ahead.
did you go to display the equation then?
So when I have the trend line toolbar out here, so that's the trend line toolbar. Do you see it?
Yeah.
And then if you scroll down to the very bottom, there's 3 things. You can actually set the intercept if you would like, where it crosses that y-axis. You don't normally mess with that. Okay? But then I just literally, to get rid of that, I can take it off and I can put it back on.
But you want us to display.
I want you to, I want you to be in the habit of giving that equation. And I also like the R squared on there, the correlation coefficient. So, cool? Questions? You guys know how to change the title, right? For that, you just click on it and go, right? All right, so I'll let you do your naming and those types of things. Go.
So do you want us to use the volumes that were given or the volumes we calculated?
I want the volumes you calculated. I use those as whole numbers, but in reality, they probably will be more fractional, like 3.1 or 3, if you guys appropriately measure, let me put it that way. Okay, so, cool? Yeah, working on measurement, learning how to measure. All right, if you guys are good with that, then I'll go on to the next part. Okay. Well, let's just minimize that. And then we'll be ready for the next hour, right? So you guys were learning these symbols, is that right? What does chemists use symbols for? Shorthand, right? These symbols are shorthands for the chemicals, and we write chemical sentences all the time. If I take hydrogen gas plus O2, that yields H2O, and it's going to be gas right now, right? Is this a sentence? It is, isn't it? And in fact, then those symbols represent something more. Now, I have a question. Many of you will know the answer to this. Is this balanced? Stoichiometrically? It's not, is it? It needs to have 2 O, and then I forgot the 2 right there, didn't I? That was an accident. That was unintentional. Okay, because I know hydrogen always forms a diatomic molecule, an element. And so I have H2 plus O2, and I need 2 of those for every one of these. Right now I have 2 for 2, so I've got to go to 4, right? Or I could have done a 1/2 oxygen. Okay, normally we'll do it in whole numbers if we can. You guys with me? There's times we would use a 1/2 right there. And so that means I need 2 over there because I have 4 and 2 there. Okay, cool. And so this is a chemical sentence where I have used element symbols to write it. Okay, that's a lot easier than writing out all of those words, isn't it? Okay, and so it also makes it easier to do the math to keep track of these things. And so, well, and this list is actually the ones that don't conform to their English names, such as potassium, which you would think would be a P, But what element is P? Phosphorus, right? And so this one took its Latin name Kalium and uses a K. Cool? All right. And then we were talking about this, that capitalization is important also. And so we want to pay attention. Note how everything up there is capitalized because it's representing those elements. All of those are single letter, but cobalt, for example, is something that has two letters, CO, right? But that second O is small, telling us that's the element. And so anyway. And then this last one, I think we were finishing on this one. If I look down here, I have calcium nitrate, right? You guys with me? And so this is how many calciums for one calcium nitrate?
1,
1. How many nitrogens?
2,
2, because there's a 2 around those parentheses. How many oxygens? 6, right? Now if I just have nitrate by itself, how many nitrates? 1 nitrate. I have 1, okay? And so you have to recognize that. And I think that most of you guys probably already have that. But that's how we use those chemical formulas. And then, what are the names of the elements that correspond to the following symbols? What about A? Together, out loud. All right, how about B? How about Hg? Mercury. How about Sr? Strontium. Yeah. Cool? All right. How about these compounds? Determine the relative number of each type of element in the following compounds. How many carbons? How many oxygens? How many phosphorus? How many chlorines? How many irons? How many oxygens? How many hydrogens? Yeah, those are all correct. So, all right. You can go through that if you would like, but we got all of those correct. All right, laws of chemical combination. We're going to calculate quantities involved in chemical combinations, and this is using classical work done by John Dalton, okay? And so a couple things you have to acknowledge, realize, believe. During chemical reactions, matter is neither created nor destroyed. Okay, that's been measured. This was not always obvious. The ashes left from a campfire may have much less mass than the wood, but where did the wood go? It left as what?
water and carbon dioxide.
Water and carbon dioxide. Absolutely. And some unburned carbon, which we call, somebody said it in here, smoke, right? Do we like smoke like in our brisket? Yeah. Okay, so just throwing it out there. Now, Antoine Lavoisier, close enough. He did some really cool experiments, and in fact, they looked like this, where he would have weight to mass. Now, he didn't have electronic balances back when he was working, I'm just going to say that. Okay? But he was able to enclose phosphorus and oxygen, and then he initiated the reaction with a magnifying glass in the sun. It's pretty clever, isn't it? So he could focus the intense energy onto the phosphorus, and then he would combust it. And what he noted was that if he contained everything, that the mass never changed. A number of other scientists, he published this, and other scientists went on to confirm this to be true. It's kind of cool, isn't it? So, in that relationship, we see the conservation of mass. And so you have to know that mass is conserved for any of this stuff I'm about to talk about to work. Okay? So we have to acknowledge that. This is actually an activity. I'll let you guys play with it if you want to. But what you can do is you can weigh this flask on the scale, and then you can add small amount to it to get the mass of that. Okay? And then you can weigh a small amount of HCl. I just put it in there. It's 50 grams. It started at 250, went to 300. And then I can actually take that and I can do start and I can do the reaction. The reaction's at the top of the page. So my two products, one is aqueous in solution. The other one is a stinky gas. Cool, you guys with me? And so then what I can do is I can weigh it again, and what I should find is that my weights are conserved, right? You with me? Even though I have new material made. And so this is for you guys to explore that. Cool? All right, so if you would like to, I will leave that for you guys to do it, and you can do it for small amounts and large amounts and see what happens. All right. Another law we actually recognize is the law of definite proportions. And so what we find is that there is a ratio of mass of each of the elements associated to compounds. And in fact, if I'm looking at pure water, which we have on the board, that ratio is 8 oxygens to 1 hydrogen. All right, 8 to 1 oxygen and hydrogen. Now, could you have gotten there by another method, by using our periodic table? You can, because if I go up and I'm looking at the symbol of hydrogen up there, right underneath that is what we would use as the atomic weight for that hydrogen, right? And how much does each hydrogen weigh? 1 unit, right? 1 atomic mass unit. And then if I go down to oxygen, how many does it weigh? 16, right? And so that means that if I have 1 oxygen and 2 hydrogens, that's 16 and 2, isn't it, in terms of mass units? You guys with me? And so if I divide that down, then what do I get to? 8 to 1, don't I? That's where that comes from. Okay? Now, what's interesting, if I look at other compounds and I see the same thing, that the proportions are there. But now, what about, let's do a proportion between carbon and oxygen, right? Now, I'm gonna do something else. I'm gonna put an X and a Y right there. Okay, you guys with me? Are there different conformations of carbon and oxygen gaseous compounds? What are the two that come to mind right off the bat? Carbon monoxide and carbon dioxide, right? Would they have different mass ratios? Yeah, they would, okay? And so in that relationship, oops, I know that one's on down here somewhere. Gosh, did I really jump that far ahead in my brain? Here it is, right? So this is showing that ratio between the carbon, and for every 1 gram of carbon and oxygen, the CO is 1.33 grams of oxygen, right? You guys with me? And for every 1 gram of carbon and CO2, there's 2.66 grams of oxygen. So sometimes when I have mixtures, would I get an in-between number? If I had both CO and CO2 present, then I could get a different number. And so experimentally this was witnessed, right? I'm trying to get to that these experiments that were done to look at not only the law of definite proportions, right, and a very similar law of multiple proportions, that those laws were done in a laboratory, in a place where we had to use the sun to initiate those reactions or other methods, and that this was very tedious work. And so I just want to illustrate that because I think that's how important it is. But this is looking at the ratios of carbon, hydrogen, and oxygen in sucrose. You guys like sucrose? I love sucrose, okay? So I don't eat near as much of it as I used to. Used to have that Mountain Dew addiction. A lot of sucrose there, right? Yeah. So carbon, 144. Now where did that 144 come from? Where did that 144 come from? That's the mass of the carbon. If I multiply, well, what's the atomic weight of carbon? 12. And how many carbons are in that? 12. And when I take 12 and I multiply it times 12, what do I get? 144. You guys see where that number came from? Yep. All right, what about this one? There are 22 hydrogens. What was the mass of hydrogen again? 1. Isn't that the best one? I mean, when you're doing atomic weights or molecular weights, hydrogens is wonderful because you just add 1 for each one, okay? So, anyway, 22. And then the oxygen is 16 times 11. Would you guys agree with that statement? And that comes up to be 176. Now, if I divide each of those, I come up with a fraction, 0.42, 0.064, and 0.515. If I take those three numbers and I add them together, what do I find? The number 1, right? I always like to look at these as a pie chart, right? And so there's 3 pieces of pie. There's the hydrogen one, and it is itty bitty, right? And then there's a about half, right? And so this is the hydrogen portion, this is the carbon portion, and this is the oxygen portion of this piece of this pie. Now, most of us like to, instead of using fractions, what are we more comfortable with? We use percentages, right? And so we would take that and we would turn that into a pie, or that's what I do. And now, sometimes are we not given every piece of the pie? We're given 2 pieces of the pie and asked to find the third one? Yeah, that's very common in science. In fact, we use that a lot where we'll know pieces of a puzzle and we'll use the pieces that we know to find the parts that we don't know, right? Very, very common in science. So we're going to do some more of this. Now, this is a great question in my mind. It's not hard to solve, but it says a 4.33 gram sample of dinitrogen monoxide, N2O, is composed of 63.65% nitrogen and 36.35% oxygen by mass. What is the percent composition of a 14.9 gram sample? It's exactly the same because of the law that we're investigating right here, right? The law of definite proportions. Okay? Cool? You guys with me? All right, what about the next one? Nitrogen monoxide, NO, has a percent composition of 46.68% nitrogen and 53.32% oxygen by mass. What possible percentages of nitrogen could be in a mixture of N2O and NO? So I've got the 2 of them together. Do we have a greater than and less than value? So if I look at the nitrogen percentages from the first question, the nitrogen could be as high as 63.65% if it were pure N2O, right? If it were pure NO, it would be 46.68. If it were a mixture, it would be somewhere between those values. You guys catch me? Catch that? All right. So these are just conceptual to help you guys understand the idea that those samples, those numbers that are given because of these laws, well, they limit things. Okay? And we can use that to our advantage and we can manipulate that. And so anyway, a lot of the chemistry that I have done in my career has been mass balances. And we're using these laws to do that, okay? So anyway, calculate the mass of a 4.75 gram sample of nitrogen monoxide, which has a percent composition of 46.68% nitrogen and 53.32% oxygen by mass. How much nitrogen is present? How much nitrogen is present? Well, it's 46.68%, right? So if I take that down to 1 and make that a fraction, that's probably the best way to do it. You guys with me? It's because there's a fractional composition. And so then if I take my 4.75 gram sample of NO times the fraction of nitrogen, right? 0.4668, right? And I hit an equal sign, wouldn't that be the nitrogen piece of that? How would I get the oxygen piece? I would either subtract what I'm going to get right here from 4.75 or multiply the 4.75 times the fraction of oxygen. You guys with me? All right. And now when I add those two numbers back together, what should they total? 4.75, right? Because the mass is conserved. We've looked at each piece of that. And 2.222 grams of nitrogen. Cool? You guys got this. Okay. Straightforward. You got it. You got it. All right. Now, I jumped to the law of multiple proportions when I was talking about CO and CO2, didn't I? All right, so we were doing definite proportions for a second, but are they really connected? They are in my mind, okay? I think they should be like together. But anyway, this is because we can have more than one ratio of nitrogen and oxygen, or carbon and oxygen, or whatever those elements may be. There's all kinds of examples of that. But now what's interesting is that they always come up as whole number ratios when we take the smallest and divide it into the largest. So up here, if you follow along, this is looking at that, and saying for every 1 gram of C and CO, there's 1.33 grams of oxygen. For every 1 gram of carbon and CO2, there's 2.66 grams of oxygen. If I take the 2.66 and divide that in with the smaller, the 1.33, and what I find is that there's a 2-to-1 ratio in that relationship. So, yeah. All right, if we do the same thing here, I'll let you guys solve this one. And so if NO consists of 14.01 grams of nitrogen and 16 grams of oxygen, whereas a sample of nitrogen dioxide, NO2 is 14 and 32, show that NO and NO2 follow the law of multiple proportions. So here's your model right here. I'll let you guys try that. So what am I doing first? We're doing nitrogen and oxygen, and we're given a relationship of 14 and 16. Or 14 and 32. First thing I do is calculate those ratios. Cool. And then what am I going to do next? I'm going to divide them, and which is going to go on top, which is going to go on bottom. We see this a lot in chemistry when we're doing mole ratios and those types of things. We divide the small into the big, trying to get the whole number ratio. Now, I have a question. Do they sometimes come out at half? So 1 to 1.5, for example. Yeah, and then if I multiply those times 2, then I have a 2 to 3 ratio. Okay, so you'll see that happen sometimes. Okay, but now in this case we're at 0.875. 6 divided by 0.328. That equals 2, doesn't it? And so there's a 2 to 1 ratio in that. And so if I calculate those ratios and then compare the 2 ratios by dividing the smaller one with the larger one, then the NO mass ratios of the compounds are whole numbers, and that fits the law of multiple proportions. Okay? Now we're going to do this more with moles during this semester. So we're going to do this same thing instead of with masses. We're going to do a whole bunch of mole ratios to find out those types of things. All right? This is like a gear shift right here. It throws us into this, and then all of a sudden it goes and turns directions, and we're going to the history of the atom. Okay? Now, there's one name that pops up right up at the beginning, and that's Dalton. Okay? Now, Dalton, literally, his was the first accepted atomic theory, okay, that was complete. And in fact, it is so much like today's theory that it's kind of uncanny in my mind, because this was 1800, somewhere around there. Okay, cool, you guys with me? So is that a long time ago? Yeah, a couple hundred years, right? So, and this is really kind of where all this started, was in this place. But he said that matter is made up of very tiny indivisible particles called atoms. Okay? Now, if we didn't have atoms, what would be the other option? If we didn't have atoms that we could divide down to, like sand, grains of sand, right? Those, once we get to a single grain, then we've hit the building block. What if we had continuous material instead of atoms? And you divided and you divided and you divided, you would never get to that limiting place. You guys with me? In fact, so when I'm talking about dividing it down to an atom, I'm talking about separating down to these elements, right? You guys with me? Now, what Dalton didn't know is that we could take those particles and actually further divide them. But if I divide any atom up here, let's say uranium, which is commonly done, right? If I divide that, then I no longer have uranium. You guys with me? Right? And I actually get some particles that are smaller than atoms. And in fact, we use those now to talk about chemistry. And so Dalton didn't know that there was a nucleus. In fact, we're going to look at that history a little bit. He didn't know there were protons, neutrons, and electrons, did he? Right? You guys need your physics joke for the day? This is for Dr. Fennell, if anybody has her. I've been trying to get somebody to tell her this joke. But are you guys familiar with the Higgs boson particle? The Higgs boson particle? It was discovered in a collider. It's actually a momentous discovery, and there's some that nickname the particle the God particle. So to explain the joke a little bit, because it sometimes needs that. All right? And so there's a little offense there, right? And so you guys know that the Higgs boson particle showed up at the Catholic Church, right? And he starts in, and the priest stops him and says, oh, you're not allowed in here. And he says, well, how can you have Mass without me? I like that one. Okay, so I don't mean that as offensive. That's supposed to be fun, right? You guys, yeah. All right. So matter, indivisible particles called atoms. Well, we know we can divide those. Each atom of a particular element has the same mass, but the mass of an atom of one element is different from the mass of another element. Would you guys agree? Is that true today? The second one? It is, right? Even the first one, when I divide farther, is no longer an atom, is it? It's subatomic particles, so, well, or maybe I can get two different. And nuclear chemistry puts a twist in this. All right, Dalton's also said atoms combine to form what we now call molecules. and they combine in small whole number ratios. Is that true? Do we take carbon and oxygen to make carbon dioxide? Yeah. Is it in a ratio? Law of multiple proportions? Yeah. Atoms of some pairs of elements can combine with each other in different small whole number ratios to form different compounds. So can I take hydrogen and oxygen and make water? Yeah. Can I take that water and recombine it to make peroxide with more hydrogen? And the answer is yes. And so Dalton saw this, published it, and it was accepted. Okay? Now, modern subatomic particles and nuclear reactions corrected the notion that atoms are indivisible. So modern atomic theory made that adjustment, and it also, the discovery of isotopes disproved that all atoms of the same element have the same mass. All right? You guys know what an isotope is? Do what? Hydrogen has 3 isotopes. The hydrogen, deuterium, and tritium, right? The hydrogen is just hydrogen. If it has an electron with it, then it would have a single electron that pairs to make H2 with the second hydrogen atom. If I have deuterium, it actually has a proton in the nucleus plus a neutron. So in hydrogen, it's just a proton. Deuterium, proton, and neutron. What do you think tritium is? A proton, 2 neutrons. And so hydrogen has a mass of 1. What does deuterium have a mass of? It's a proton plus a neutron. Each have a 1 mass unit. It's 2. And when I get to tritium, what's its mass? 3. Okay? And so that's a very obvious example. When we get into elements all around the periodic table, such as fluorine. Fluorine-19 is the most common isotope, but there's other variations of that. Okay? So, and we'll talk about how we get to those mass numbers with the ratioing the common isotopes. All right. So Dalton's theory and the law of conservation of mass. And so this fits perfectly. Atoms combine to form compounds. Atoms do not break down and are not built out of nothing. They merely exchange partners to form new compounds, and therefore mass is conserved during chemical reactions. So his theory supported the laws and what was found. It also fit with definite proportions, that atoms combine to form compounds in small whole number ratios, and specific elements are in specific ratios. And those all samples of pure compounds have identical proportions by mass. And so, well, that's pretty close to right. So anyway, the last one, law of multiple proportions. Atoms of some pairs of elements can combine with each other in different small whole number ratios. So there was using that. And then when atoms of the same 2 elements combine in different ratios to form different compounds, if the mass of one element is held constant, the ratio of masses of the other element must be in a whole number ratio. Okay, so all of these things were witnessed, and so that's why Dalton's theory was accepted. Yeah. Now, we move on to another physicist. I notice we're, chemistry, physics. Are those closely related? Yeah. I think of physics as the ingredients and chemistry is mixing those together to make a cake, right? And then the biologists stand there and say, well, that looks good. They observe it, right? Oh, that's icing on the outside. Let's cut it open, do an autopsy, and see what's on the inside, okay? And so those are kind of the 3 fields in cake analogy. But this particular physicist, J.J. Thomson, now if you look at his academic tree, his family, they make academic genealogies. His is massive. This man influenced physics probably as much or more than as much as anyone. Okay, and so he did some really cool work. He built a tube, a cathode ray tube. Now that sounds kind of cool, doesn't it? And so a cathode is a device. This is a kind of a cartoon picture of it. This is an evacuated chamber. Okay, it's in high vacuum. You guys with me? So all the molecules have been removed from it, or as much as they could at the time. You guys, so they put it on a vacuum pump, suck all the air out. Now, if I tap that glass with a hammer, what would happen? It would implode, wouldn't it? Okay, because it's under a vacuum. And so, but he built these chambers, and then he took a high voltage source and he put in plates, and when you put a charge across these two metal plates and drill a hole in the center, and it would create what was called, well, a ray, right? A cathode ray. So the cathode side allows electron beam to form, and then that beam shot down to the end of the chamber. You guys with me? All right. Now, this portion of it is called the magnetic sector. Okay, and in fact, modern mass spectrometers use magnetic sectors in the same fashion to separate and identify the masses of atoms and molecules. All right, kind of cool. Now, but what he did was he put in charged plates in that magnetic sector, and then he could vary the voltage of those charged plates. And what it did was it changed the magnitude of the field, right, based on voltage. And so he would know the magnitude of the voltage change, and then he would look at how the particle, when it wasn't affected by the magnetic field, it would travel in a straight line, and when he would put it on there, it would bend. This was a phosphorescent surface. He could see the distance that the bend or what occurred based on the different charge. And so, well, actually what he got was a mass to charge ratio for the electron. A mass to charge ratio for the electron. Okay? Now, wow, that's kind of cool, right? Now, there's another scientist who followed him, and his name was Robert Millikan. Okay, Robert Millikan. Now, this experiment, I'm going to go to it pretty quickly because we're about to run out of time, is quite crazy, all right? This experiment, he took a can, and he drilled a small hole in a divider plate, and that plate he put a charge on, positive charge. This plate he put a negative charge on. And then, you guys know the effect of rubbing a balloon on your hair, it causes it to become staticky, right? The same thing happens to small particles. When they are pushed, they strip electrons and they move from one particle to another, so I can get a higher charge density on small particles. And so what he did was he misted that in there, and he caused that to have those charges. In some cases, even used an X-ray source to do that. But then, negatively, he would allow some of those to drop into the bottom chamber. Right? You guys with me? And then he would vary the charge on the plates and observe the drops in the microscope, count those, how they would suspend. And from that, he actually, which is just, I mean, it's crazy, all right? But what he found was the total charge of the drops was a multiple of 1.6 times 10 to the negative 19 coulombs, the charge of a single electron. Now, if you have the mass to charge ratio and you've now determined the charge, what else do you have for the electron? You've got mass, don't you? Because you have the mass to charge, you know the charge, and so Millikan is credited with the charge of an electron and its mass, well, combined with the first experiment. This is amazing, guys. Okay, this is cool science. So I'll let you go. It's a Friday afternoon, and I'm a minute over, so please forgive me for that.
Actually, with JJ's.